All right, AP Statters, this is it, our eighth and final part of our summer work. We're jumping in. We're going to kind of review binomial, but we're going to add in a different thing that's kind of binomial-ish, but totally different, but kind of the same. So binomial geometric probabilities. Let's jump in. Mean and standard deviation of a binomial random variable. So remember last time we went into our green sheets, right? Or whatever color yours is. And we found the binomial distribution and the binomial formula right here. Well, right next to it, we've got a little formula. And if I look up, that's the mean. This is the mean of a binomial distribution. This right here is the standard deviation of a binomial distribution. Okay. So those are going to be useful. We need to know where they are. But let's go ahead and write them in. So mean of a binomial distribution, mean of the number of successes is equal to, all right, so mean of number of successes, mean of X is equal to N times P. All right, N is our trial size, right? Trial size. And P is our probability of a success. Cool. That's it. Pretty easy. The standard deviation is, and you can see it on your formula sheet, the square root of n times p times 1 minus p. Okay, so this is number of trials, probability of success times the probability of failure. Multiply all those three together, square root it, and you got it. That's it. Easy peasy. All right. Independence assumptions. So there's a 10% rule. How do we know if it passed the bins thing? In real life situation, it's difficult to sample with replacement, which in turn affects the probability of something happening. So basically the idea is this: the population must be large enough to support the sample size. All right, so imagine this. You have a bowl full of 20 Skittles. Think about the probability of pulling out an orange, right? An orange Skittle. That's probably, I don't know, 1 out of 4, 1 out of 5, right? If I take a sample of, if I get an orange one, right? If there's, let's say 5 out of 20 are orange, when I take out that orange one, I can't put it back in. So now the probability is 4 out of 19. If I get another orange, now the probability is 3 out of 18. The probability is changing quite a bit each time, right? So every time I pull one, the probability is changing. So it's not independent. Imagine though, if I had a bowl of 200,000, right? And I take out one orange one and there were like 50,000 orange ones in there. Now I have, 49,999 out of, 200,000. The probability hasn't changed very much, right? So I need my population to be big enough to take a sample out. So if my sample here was size 5, that could change the probabilities a lot. If my sample size is just 5 here, it's not going to affect the population, or it's not going to affect the probability of the success very much, right? So that's where they came up with the 10% rule. 10% rule looks like this: 10 times the sample size needs to be less than or equal to the population size. Okay, so 10 times the sample size, or trial number, right? In this case, sample size. And then this needs to be the population size. Okay, easy peasy. So, let's see. Let's see. A company produces processing chips for cell phones. At one of its large factory, they produce 10,000 chips a day. 2% of the chips produced are defective in some way. A quality check involves randomly selecting and testing 500 chips. What are the mean and standard deviation of the number of defective processing chips in these samples? So let's do our checks, make sure we're okay. Is it binomial? Yes. It is either defective or it is okay. So there's only two options. So binomial, fine. Independence, let's check our 10 and less than the population. So 10 times 500 chips, that was our sample size. Is that less than the 10,000? Yes, it is, right? Because that's 5,000 is less than 10,000. So we're okay for independence. Um, my N is the sample size is the same. Yes, it is. 500 is the sample size. And then S, is it the same probability? Yes, 0.02 are defective, and that's going to stay the same. Okay, cool. So let's find the mean and the standard deviation of this. So the mean number of defective will equal my sample size times the probability, right? There we go. I think that's going to be 10. So 10 defective chips on average. Will it always be 10? No, it's gonna vary, right? But on average, we should get about 10. Standard deviation of X is equal to the square root of N times P times 1 minus P, or the complement of this. So if that's 2%, that's 98%. Cool. I plugged that in my calculator, and that's 3.13-ish defective chips. There we go. So on average, we have 10. We wouldn't be surprised if we had between like 7 and 13 would be kind of the usual range we would get out of 500. If we got outside of that, if we got to 20 defective chips, that would be pretty surprising. That's over 3 standard deviations away, right? So that's kind of how we use these mean and the standard deviation to decide if something is going wrong with this manufacturing process. We'll be doing that later. All right, geometric random variables. So geometric is like binomial in some ways. The big difference for geometric, the big difference is how many times, well, I can't even spell how many uh, trials tell the first success. Okay. Binomial is I shoot 10 free throws, right? Geometric would be I shoot free throws until I make the first one. Okay. And then how long did it take for me to do that? That's what geometric measures. All right. So geometric probability formula. Well, guess what? Also on our green sheet right here, right? Um, and oh man, I kind of want to do a problem first, but um, yeah, let's just do a problem first. Let's go down here. An airline claims that there's a 10% probability that a coach class ticket holder who flies frequently upgraded to first class. We had this one last time. The outcome is independent from flight to flight. Sam is a frequent flyer who always purchases coach class ticket. Let F equal the flight number where Sam gets his first upgrade. So we're trying to find how many flights he takes until he finally gets a successful one, right? So what is the probability that his first upgrade occurs on his third flight? So probability that X is equal to 3. His first success is the third flight. That's what this means. Probably X equals 3. Well, what would have to happen? Oh my gosh, I need to put that on the screen. There you go. What would have to happen for that to happen? Well, he would have to be unsuccessful in the first time. There's a 90% chance of that happening. He would have to be unsuccessful again. There's a 90% chance of that happening. And then finally, he would have to be successful, right? So he has 2 failures, 2 fails, and then he finally has 1 success, right? We could rewrite that as 0.9 squared times 0.1. Okay, so here's the geometric probability formula from what we have here. Let's write that in. So we see the word geometric here, right? Probably the X equals little x is equal to, and 1 minus the probability of a success to the X minus 1 times the probability of a success. Well, how does that make sense? Well, if we say the third trial, like we did here, right? Probably X is the third. So the third trial is the first success. We would have 1 minus the probability of a success. That's it right there. So probability of a failure, right? So this is probability of a failure, probability of fail. And then this is how many times it's failing. It's failing 1 less than X, right? We failed 3 minus 2 times in this problem. 3 minus 2 is 2. So 2 failures. And then this is your probability of success, probability of success. So that's your first success. So 1 success, and the ones before it were failures. That's what this probability formula means. Makes sense. It's exactly what we did here. Okay. The mean of a geometric random variable, again, if we go to random variables, right? Geometric, the mean is just 1 over p. Okay. There's a standard deviation as well. We don't use this very often, but it is here just in case. I've never seen it used before, but know that it's here just in case they ever ask. So we're just going to go over the mean. The mean of a geometric random variable is just 1 over the probability of success. Okay. I don't know if I go over that. In this problem here, we'd have 1 over 0.1, which is 10. So on average, we would expect 10 trials before his first success on average, right? That's what that is. Cool, cool. All right, let's keep going. What is the probability that Sam's first upgrade occurs after his third flight? Oh, well, let me show you something. I forgot to show you the calculator way. We don't always want to do this, right? Because that can take a lot. So on the calculator, we're going to go in, same place we've gone before. Oops. There we go. We're going to go to second vars or distributions. We're going to find geometric PDF. There it is, geometric PDF. All it's asking for is the probability of success and what number it was successful on. So 0.1, so 10% chance of success, and we want to know successful on the third attempt. There it is, 0.081. Yeah. I bet you if I did 0.9 squared times 0.1, oops, 0.9 squared times 0.1, there we go. We get exactly the same thing. Yeah, nice. So, sorry, P is the probability of success. X is equal to 3 for success on the third trial. We plug it in, we get 0.081, which is exactly what we had here. Cool. All right, so now let's move along. What is the probability that Sam's first upgrade occurs after the third flight? So after the third flight. So he flies once, twice, 3 times, and then sometime after that, the fourth, the fifth, the sixth, the seventh flight, he gets it. So we want to add all of these up. Do you remember geometric CDF? All right. Oh, sorry. It is geometric CDF. Do you remember binomial CDF? Yeah. So what we want to do is cut out these, right? So it's going to be 1 minus, this is geometric CDF this time because we are accumulating. And it's going to be the probability of success, 0.1. And then we're cutting out 3 and below. So I'll do 3. So here we go. 1 minus geometric CDF. Say 1 minus geometric CDF, 0.1, and we're doing 3. 0.729. 0.729. About a 73% chance that the first make is after the third flight. Cool. How many flights would you expect on average for Sam to need until he gets his first upgrade? Well, that's going to be the mean, right? And that's just 1 over P. So in this case, it's 1 over 0.1, which is 10. So we would expect on average 10 flights for him to get his first upgrade. If we had to find the standard deviation, of course, it just looks like the square root of probability of failure over the probability of success. Again, this will always be there for you in case they ask. Very, very rare. I've never seen it. All right, so here we go. Let's get a little review. Binomial and geometric. Okay, binomial, there's a set trial size. For geometric, it's how many tries till first success. Whenever we see at least, we're going to go 1 minus the probability of something, right? Because that's going to be to the right. PDF and CDF. PDF is 1 outcome, only 1. CDF accumulates from the left side for binomial and geometric. Okie dokies. All right. Let's see. Moving on. Oh, we're at additional problems. I think this is it. All right. So if you want to stick around, that's cool. If you want to save these for studying, that's fine. But let's jump on in. I don't think I have the probabilities for these. So I'm going to pause and get those for you. One sec. All right, here we go. Probably makes exactly 5 out of 10 free throws. Should be 0.026. You can get that a couple of different ways. You should be able to use the binomial formula, know how it works, explain to somebody how it works. Should be able to find out what this means. We have 5 successes and 5 failures. Boom, boom, boom. You could also use binomial PDF, 10.2 and 5. Okay, so either one of those gets you that. All right, probably makes less than 4 out of 10. I believe should be 0.879 or something like that. I wouldn't, I mean, you could do a formula, but you'd have, 4 PDFs to add together, right? So let's just do binomial CDF. It's less than 4. So if you made a mistake, it's probably this. Less than 4 is 3 and below, right? 4 is not less than 4, it's equal to 4. So less than 4 would be 3 or less. So you'd have 10.2 and 3. That would be less than. All right. And that'll give you that. Find the probability he makes more than 2 out of 10. More than 2 out of 10. So that'd be 3, 4, 5 that we want. We want 2 and below. So that's going to be 1 minus, oh no, sorry. Oh yeah, he makes more than, my bad. More than 2 out of 10. More than 2 out of 10. So that's 3, 4, 5 and above. So that is 1 minus. Binomial CDF 10 comma 0.2 comma, we're cutting out 2 and below. So I'm going to do that. And our answer should be 0.322. All right. If he takes 10 3-pointers, what is expected number of makes and the standard deviation of makes? So if he takes 10, what would be expected? So the mean X is going to be 10 times 0.2. He's a 20% shooter. He takes 10. Should make 2 of them on average. The standard deviation of makes is going to be root n times p times 1 minus p. So that, and I think that ended up being like 1.26 makes. Cool, cool. So he wouldn't be surprised if he made 1, 2, or 3. Once he gets beyond that, you start getting surprised. What is probably his first make is his third attempt. So first make, as soon as you see that, you know you're doing geometric. It's exactly his third attempt. So to make that happen, probably that X is equal to 3. We're going to have 2 failures. So 0.8 squared times first success, and that happens once, right? We can also use, geometric PDF, because this is happening just one time. We want exactly one outcome. And we're putting in the probability and the first success being the third time. And I think we end up getting 0.13 or somewhere thereabouts. First make is one of his first 4 attempts. So 1, 2, 3, 4, but not above. So we're looking for this. So that's good. That's normal CDF, accumulates to the left. So this is going to be geometric CDF. And we're going 0.2 comma 4. So it'll add 4, 3, 2, 1 all together. There is no 0 in geometric because you can't have a success on your 0th try. You can have success on your first try. Find the probability that his first make is after this 4th attempt. Oh my gosh. So 1, 2, 3, 4, 5 and above. Oh, did I get you the probability for the one above? Okay, let's go back to 6. Probability for that one is 0.59. Well, this is 5 and above, so it's the complement of this one, right? So it's going to be 1 minus geometric CDF 0.24. So if this is 59%, this will be 41%, so 0.1. And last one, what is the average number of shots he takes to get his first make? All right, so if he has a 20% chance, the average number of shots for his first make would be 1 over the probability, 1 over 0.2, multiply top and bottom by 5. We get 5 over 1, so 5 shots on average we would expect until he gets his first make. Cool, cool. That's it, people. Summer work done. All right, so there are a couple of or at least one practice test for you to do in there. Review, and be ready. We'll see y'all later. Bye.